up. It's Pooja from NVIDIA. Can we click on there? Yeah, sure.
Even with this, and they reach my people. Yeah.
All right. Good morning, everybody. Very excited to be here. I'm Pooja Rao. I'm a quantum algorithm engineer at NVIDIA. That means on a day-to-day basis, I take algorithms, I implement algorithms on quantum hardware, but not really, like on quantum simulators most of the times. And today I'll talk about accelerated quantum supercomputing for building scalable applications. So I'm going to talk about what it is and are we there yet? And what tools do we need in order to get there? And once we get there and while we are getting there, what kind of applications can we build that can leverage maybe AI supercomputing or other things that we have available to us right now. The focus really is going to be on the generative quantum eigensolver, which is this framework which combines Gen AI to compute ground state energies. But essentially, it's more general than that. It's a paradigm to generate quantum circuits leveraging Gen AI. All right, so this is the rough division of my parts. It's not a very informative outline, but I'm going to start out by describing what accelerated quantum supercomputing is. And I'll give you a very top-down approach. I'm an application scientist. I'm not a hardware engineer by any means. But the goal is to convey what this paradigm really is, where does NVIDIA fit into quantum computing ecosystem, and what we are doing to enable the quantum computing ecosystem. Then, of course, focus on the generative quantum eigensolver. Talk about what this algorithm is, compare it with something, the VQE solver, right, that everyone kind of understands, compare the framework to that kind of algorithm, and talk about how you can make some tweaks in the changes of the GQE to extend it to your own problems. I'll share where to find the publicly available code in case you are interested in getting some hands-on experience. And then I'll talk about some of the work that's been done in the community to extend it to other areas and domains. All right. So NVIDIA has been at the forefront of a lot of computing innovations in the last couple of decades or so, and not only been at the forefront, but has enabled those revolutions. And obviously, GPUs have been at the front and center of it, but CUDA has played a huge part in all of this as well. Right? For those of you unfamiliar, CUDA provides this unified programming environment where you can program both CPUs and GPUs from the same application program. So it can handle heterogeneous architectures consisting of CPUs and GPUs. For example, I have this, you can think of this as like an image processing application where you want to pull in the data, a task that is more appropriate for a CPU, and then you want to make some changes to it. Again, maybe you want to call in a CPU for that, but then you want to do the compute-heavy part on a GPU. For example, you might want to run CNNs or a diffusion model or something else. And you typically leverage some library called PyTorch or TensorFlow, but underneath all of these libraries called cuDNN, they might call cuDNN, which eventually calls CUDA underneath all of this. So CUDA is accelerating a lot of like AI workflows and has been tremendously effective in that heterogeneous compute and scalability. And of course, for scientific computing, cuBLAS is one such library. So the main point here is that the heterogeneous compute and CUDA enabling an entire set of libraries in different domains. But how is NVIDIA enabling the quantum system if we are not building any qubits, right? But we are building all the accelerated quantum supercomputers. Now, what are those accelerated quantum supercomputers? So at a high level view, it could look something like this. So you can view that quantum is part of this larger workflow, right? All useful quantum computing devices are not just going to be quantum hardware, but they are going to be, a quantum hardware is going to be absorbed into a larger supercomputing ecosystem. It's a very well-established thing now. There are a lot of great work being done at the supercomputing centers, including at NERSC here and a lot of other DOE labs, as well as at NVIDIA. But you can imagine, as an application scientist, you have access to all these GPUs and a bunch of QPUs, and you want to be able to do things like distributed model of quantum computation, right? So you want to enable, you want a software that can enable this kind of computation and is very effective at programming these different hardware components in kind of like a seamless way. And one more thing here is that when you absorb a quantum hardware or some sort of QPU into your supercomputing setup, it could be, it just doesn't have to be a hardware of a single modality, right? It could be a combination of different modalities. So you also need something that is QPU agnostic. All right. So we are not there at quite there as far as the accelerated quantum supercomputing is concerned, that there are huge leaps that are being made, but we are still kind of at the phase where we are iterating on better qubit design. We are trying to come up with better hardware. We are figuring it out what algorithms would be appropriate for such hardware. And of course, there's a lot of really great work being done in quantum error correction. There are really great EI decoders out there that are being refined and being worked on. And there are also infrastructure challenges, like how do you connect all these different parts, like what kind of latency does it require, et cetera, et cetera. So I want to focus mainly on hybrid algorithms today. And I want to focus on how AI supercomputing can enable such hardware. But I do want to give a shout out to the work being done with regards to designing better chips. NERSC had some really great results using 7,000 GPUs. It was one of the most comprehensive simulations, and it was announced a couple of days back at GTC DC. So really great work being done at NERSC as well. So as far as hardware is concerned, and this is something I don't know deeply, but I kind of know a little bit, and it was announced a couple of days back. So NVIDIA is building NVQLink, which is an open and universal architecture to connect these different hardware components. NERSC is one of the starting partners, and these partners are not just passive partners. They help us define the spec for such a reference architecture, and obviously are the initial adopters for such an architecture. And in the picture here, you can see the GB200 system connected with some of our quantum controller friends here. There's a white paper that came out last night or early this morning in case you're interested in checking out about this architecture a little bit more. All right, but let's come back to the software tool that we require to actually program these kind of heterogeneous architecture. So leveraging the experience that we have from building CUDA, NVIDIA has CUDA Quantum, which is a open source programming model that can handle QPU, GPU, and CPU compute from one place. We have a great simulator, tensor network-based simulators, as well as like state vector simulators, noise simulators who are doing noisy simulations, as well as we have integration with all qubit modalities with photonics, superconducting, neutral atom, trapped ion, et cetera, et cetera. So we support the QPU builders very widely. It has this, so similar to CUDA, for those of you who come from that world, CUDA Quantum has a kernel kernel approach to things, meaning that you have these specialized functions called kernels, and whatever you write, the code that you write within the kernels get offloaded to this special accelerator or the quantum machine in this case. One important distinction with CUDA, however, it's completely open source where CUDA is not. So you can pull this programming model, build your own simulator, or integrate with your own simulator, or build your own applications. So it's completely open for you to experiment and play around with. And of course, we have, it's meant to be highly interoperable with other CUDA-X libraries, meaning with cuDNN or PyTorch or TensorFlow, anything that's built on top of CUDA. So we have these domain-specific libraries within CUDA, CUDA-Q. So for example, for quantum error correction, we have the CUDA-Q QEC. And for material science or chemistry, we have something called CUDA-Q solvers. And in fact, the GQE code that I'll be talking about today is can be found under this CUDA-Q solvers library. Right. So these are some of the examples of the kind of workflows that you can run with AI for quantum computing. There's a paper in the middle. I have a screenshot of the paper. It's been, you can find it on arXiv to read more about these kind of algorithms and the work that's been done in this field. It's been accepted for publication in Nature Communication and will be out there sometime soon. But if you want to find it, you can find it on arXiv as well. There's a whole bunch of papers from NVIDIA team, and not just NVIDIA team, but people in the community that have taken up this field and are coming up with algorithms that are super innovative and can leverage the advances in AI effectively for quantum. All right, so before I introduce GQE, let me talk about the variational quantum algorithm that most of us understand, right? So the basic idea here is that you have this hybrid quantum classical setup, right? And back in 2014, when it came out, it was a path-breaking algorithm because you had algorithms like QPE, which were very promising, but the depth was very prohibitive, among other things. And what this algorithm proposed was parameterizing some trial state and then training the trial state so that you can find these ground state energies, right? And it's still being actively researched into to this day, but the optimization kind of becomes a problem, right? So for example, you need to find an appropriate starting point. You might get stuck in local minima, and there are some mitigation techniques suggested for that. But as you scale up, the problems become more and more, right? One such kind of like limiting problem is the barren plateau problem. Essentially, what happens at higher number of qubits, your landscape, your optimization landscape becomes more and more flattened, and then the optimizer fails to converge. And of course, efficiently loading classical data is inherently a very, very challenging problem. And if you're trying to do a problem which requires that, it adds another layer of complexity to that. So is there something that we can design that can have some similar parameterization stuff, but can maybe converge a little bit better? So that was the whole idea with GQE, and the workflow compared to VQE looks something like this. So now the parameterization has been entirely pushed on the classical side, right? So you run these parameterized classical models, and I'll talk a little bit more about what specifically that classical model is. And then you generate these circuits, and then you run those circuits, feed that back into your classical models, and that's how you train your parameters, right? And the idea is that you can get around some of the training problems that are inherent to the quantum parameterized circuits. And of course, LLMs have been very, very successful in the last few years. Particularly the GPT model has been extremely successful. So let's see if we can draw an analogy between generating quantum circuits and generating text and kind of build on that, right? So you can think of quantum gates as words, and you can think of a set of quantum gates as your vocabulary, right? So that set of quantum gates could be your hardware native gates, or that set of quantum gates could be more appropriate for more specific to your domain problem. So for example, if you're trying to do quantum chemistry stuff, that set of gates might be your UCCSD ansatz pool or something like that. But what we are doing is we can design this framework so that your LLM produces this sequence of gates or these sentences, if you will, which are circuits, and you can run these circuits and you can see if your cost function is moving in the right direction or not. And based on that, you can train your parameters, right? And the whole idea is to leverage the scalability that has already that the classical world has already utilized very effectively. So we have something called operator pool, which is equivalent to vocabulary here. All right, so this is a little bit more specifically what the training process looks like. So you start out with the transformer, which spits out a bunch of circuits. So at every step, you have this batch of circuits, or it produces a few sentences, if you will. You compute the cost function with respect to each of these. And we use something called a GRPO loss. And for those of you who are into the AI world, this was a loss function that was suggested by the DeepSeek paper. It's in the DeepSeek math. And that's actually, that's a very good example of how you can leverage advances in a very different field, which is super active and can help with workflows like these. So you generate basically these circuits, you compute a cost function, and what GRPO does, it stands for Group Relative Policy Optimization, if I'm getting it right. But the idea is that instead of like looking at the absolute value of your expectation value from each circuit, you kind of grade them, right? So you compute a group average, and you compare each of the expectation value from your circuit to that average. So either you do better than the average or you do worse than the average. So you kind of have a scale. And then you use that, you feed that back into your transformer, and you adjust the weights accordingly. So this reinforcement learning based method actually gives you better convergence, and it fixed some of the chemical accuracy problems that we were having with a slightly different loss function. So since it's mostly a classical optimization problem at this point, you do similar things like discarding 5% of the data to avoid things like overfitting, et cetera, et cetera. All right, so I'll present some of the benchmarking results that we have from running it on simulators, as well as a couple of hardware, quantum hardware results as well. So this is running it for an H2 problem using the UCCSD ansatz pool, which basically means we have operators that look something like this exponentiated Pauli, where T stands for a time, and we take discretized time for this, for these purposes. But you can compare it with the correct answer, which stands for FCI, and you can see how the model performs. It seems to produce chemically accurate results for this small system. So let's crank up the knob a little bit and see what it does when you increase the qubit size. Right, so these are for LIH, BEH2, and DO, and CO2. So here I'm just comparing chemical accuracy across these four systems. And in the next slide, I'll talk about the associated computational cost. So in all of these four examples, the GQE or GPT-QE, which is a special instance of GQE, achieves the chemical accuracy. So this is a little bit more computationally oriented. You can compare the computational cost associated with different methods, particularly with VQE and GQE. So you can see that there's a couple of things to see here, but mainly this is the main number that you should be paying attention to. And this roughly corresponds to how much for all the iterations combined, or for all the epochs combined, how many operators are being used. And each operator, obviously, further, you can roll it down into a sequence of CNOT gates and a rotation gate in the middle. But it corresponds to the operator that I showed a couple of slides back, this EIPJT. So you can see VQE is 400K for the 12 qubit simulation as opposed to 25K for GQE. For, again, the 12 qubit N2 simulations, it's 750K versus the 150K. And for the 18 qubit CO2 simulations, it's 10,000K, which is about 10 million, I think, compared to 250K for GQE. So huge savings in cost and much faster convergence. All right, so this seems great and very, very promising. But can we do better in training? Like, how do we train for other systems? Like, what other tweaks you can make here and there in training loss, operator pool, to customize it to what we want? Oh, actually, before we go into that, I mentioned this briefly, that this GRPO loss function was something that we adopted more recently. Last year, when the paper came out, we actually used only the logit matching, and you can see how much improvement there has been adopting this GRPO loss function. Anyway, actually, one more thing about the parallelization opportunity. So I talked about, in a batch, you produce a bunch of sentences or a bunch of circuits in parallel, and that's part of the optimization process, that it helps the transformer learn faster, what direction to move things in, right? We have this distributed model of computation in CUDA Quantum, where you can distribute all of these circuits asynchronously and in parallel using CUDA Quantum, and that's what we've utilized. And based on that, compared to CPU with just a single GPU, we were getting 40x. But doing this embarrassingly parallel optimization, we got an almost 8-fold increase by putting it on 8 GPUs, essentially. And that made all the difference. I think the simulations that were taking like a couple of days to run, they just ran in like 45 minutes. It was amazing. So this is the work that was done by a group in Japan, where they took GQE, did some error mitigation stuff, and actually ran it on IBM quantum hardware. And again, getting pretty good results. And Quantinuum has recently announced that they were able to actually train the GPT model in their system. So in case you're interested in learning more about that, please check that out. All right, so coming back to this stuff. So how do we change some of the training? How do we play around with the training a little bit to maybe improve the training, maybe to learn or compute ground state energies, or do something where the molecular system is close to what we already have data for? Or how do we tackle a problem which is different than the quantum chemistry problem, right? So if you are thinking about tackling a different problem than the quantum chemistry problem, again, you can start out with a different operator pool. And if you're trying to do, let's say, trying to go down the route where you have you're essentially using pre-training and transfer learning. Let's say the idea is that, let's say you have data for your current model, pre-trained data for your current model. You can leverage that data. You can have an encoder-decoder type setup in your transformer model, where your encoder can take the data from your current problem and give you more specific results for your problem, right? So one thing I kind of did not mention when I was talking about this architecture with GQE initially, what we had used initially was just a decoder type model, meaning that we don't specify any particular inputs in the model. It just learns completely based on the feedback that we give. But you can have a more advanced transformer models, right? And these kind of transformer model already exist in the classical community. For example, an encoder and decoder type model, where you can put things like conditional input into your model and do things like transfer learning. For example, there's a group in China who are using that similarity between molecules using the SMILES representation, so textual similarity between molecules in this kind of architecture to train their model. And there are people using graphical similarities between model to train other molecules as well. I'm not a quantum chemistry expert, so I don't know the specifics of what molecules and whatnot, but the ideas of encoder, decoder are being exploited in the community. All right, I think I'm pretty much out of time at this rate, but these are some of the other works and related papers that are being investigated in the community. And with that, thank you so much.